First of all, is timeline analysis. Just briefly, during a forensic investigation, it's often useful to know what events occurred over time, including when files were written, when websites were accessed, and so on. So timeline analysis is the process of collecting event information, use timestamps from the file system when files were created and modified and so on, and registry files, log files, web browser history and cookies, cache files and so on. Those are then collated into a super timeline of all the events on the system. There's tools such as Timeline that will do this automatically. If you give them a disk image, it will go through and search for all the events that can collate into a super timeline. One of the issues in timeline analysis is that individually, many of these sources can be easily destroyed by, for example, clearing your web browser cache, or forged by generating fake timestamps or fake log file entries. So it's desirable to get as many possible sources of timeline information to corroborate each other. So the Zettabyte File System. It's very different to most traditional file systems. Traditional file systems, you have one file system sitting on one disk or one partition of a disk. If you want some sort of redundancy in case of disk failure, then you need to create a volume, like a mirror volume or RAID, that presents to the file system as a sort of abstraction of a disk. So the file system itself isn't aware of the level of redundancy. This has a lot of problems, especially with large deployments, because everything's all fixed once it's created. You can't just add disks, and you can't just you can't just add disks. The level of redundancy is fixed once you create a volume. You can't fine-tune things, and you can have some file systems that are taking up very little space that are allocated to a disk, whereas there's other file systems you need more space. So that can require you to migrate file systems, which is very time-consuming. So ZFS uses a very different approach. All disks are added to a pool, and then file systems are created virtually on top of the pool. Creating a file system in ZFS is a bit like creating a directory in a traditional file system. It's got many advantages over traditional volume-based management. You can always just add disks if you need more space, and since file systems all share the pool space, you can easily have a file system or an individual file that spans multiple disks. It's larger than multiple disks. But because it's very different, many existing forensic tools can't analyze ZFS disks. Internally, how ZFS works, everything's an object in a tree. There's each pointer to a new object can actually contain up to 3 pointers, which then point to up to 3 identical copies of the child object, and they can be spread across different disks in the pool to provide redundancy in case an individual disk fails. The triple pointer structure also has a checksum in it, which allows ZFS to detect if any of those objects have been corrupted. If it has been corrupted, then ZFS will find one of the other copies, see if that's good, and then replace the bad copy. So it automatically heals from disk corruption. The tree itself is updated using a copy-on-write atomic transaction. So the tree can't ever be in an inconsistent state. It moves atomically from one state to the next. Because of the redundancy and because of the redundancy and checksums and copy-on-write, the ZFS provides guaranteed integrity up to a point. For example, if you create it with redundancy, with triple redundancy across 3 disks, then you can guarantee that 2 of those disks can fail and you won't lose any of your data. You also won't lose any data in power failure or so because it's atomic transactions. So, as I said, it's very scalable. ZFS is very popular for data center storage because it's very scalable and flexible. You can have up to 18 billion devices. Files up to 2 to the 64 bytes large. The total disks allocation will fall up to 2 to 72, 256 bytes. as I said, guaranteed data integrity with recovery. Because everything is already copy on write, snapshots can be implemented very efficiently in ZFS, and they're widely used to provide recovery. Remote replication as well. That's used by many cloud providers to replicate file systems to different machines. It can be done very efficiently, again, because it's copy on write. When the replication operation is underway, you don't have to worry about keeping track of the old data because ZFS has to do that already. Individual objects can also be compressed and deduplicated, and you can fine-tune the redundancy on them. So you can fine-tune the level of redundancy you want on things, or the amount of compression right down to the individual file. Because it's open source software, it's widely used in Unix systems. It's common for servers. There's network storage devices from Oracle, Netgear, Raptop, Arc Systems, many other providers. Some on the back of my t-shirt too. It comes pre-installed in many commercial network storage devices that you just plug in and it acts like a Samba server or a CIF server. It's also used as the cloud backend for many cloud storage providers, including Joint, Delta, Center. It's rumored to be used by Google as well, but they haven't sort of confirmed that. But they're known to have people who use who are FreeBSD and ZFS experts on this stuff. So there's very little existing ZFS forensic research. The most well-known article is just this one, but column B, as well. It's an overview of ZFS forensics, very general overview. Talks about some of the things that make it easier, like having the copy and write, having multiple copies of things, some of the things that make it more difficult. It's based just on examination of the documentation and the source code, so it's purely theoretical. There's no analysis of actual file systems on disks. There's only really three other publications on ZFS forensics. Max Bruning did a presentation on the ZFS on disk data work, where it shows how to access files and data on the ZFS file system from first principles using a debugger. He's also published a blog post about using the same techniques, like using the debugger to recover deleted files and so on. A student at Macquarie University wrote an enhancement to the debugger for locating known data within a disk that's useful for some sorts of data recovery forensics, but it's not really applicable to timeline analysis. There's also a publication in the Spanish version of the IEEE transactions about some anti-forensics techniques in ZFS. That's all about hiding evidence. Now we'll talk about my research. First, the objective to determine what sort of timeline information I can get from the ZFS's internal structures and how long that's retaining. For example, some data might be quickly overwritten. Unlike Beebe study, I want to do empirical analysis based on actual file systems written to actual disks, not purely theoretical. I hope by doing this I can determine at least one technique for verifying false file timestamps by using the internal metadata. And I want all this research to provide a basis to develop new forensic timeline tools for ZFS, because there are no existing tools. So I'll very briefly go over the experiments. I created ZFS cores with between 1 and 9 disks in a variety of configurations. I developed a file activity simulator based on statistics from core network storage, and we used that to simulate file activity on each pool for 24 hours. For each different configuration, there was at least 3 experiments. One control, where there was no falsification of timestamps. One where I used changing the system clock to while the file was saved to revert the timestamp. Because there was some unusual behavior in large files that I discovered was very useful for forensic purposes. In total, there was over 110 gigabytes of ZFS data. These are the structures. First of all, the Uber blocks. The Uber blocks are the structures that are at the top of the object tree, the root of the tree. Block pointers are the pointer structure, which contains the triple pointers to redundant copies of objects and checksum and some other metadata. I looked at the file objects themselves, which contain the file attributes and so on. And I also looked at space maps, which are an internal object that ZFS uses to store its free space data. go over these structures in detail. First of all, Uber blocks. They contain a transaction group ID, usually TXT, and a timestamp. So they provide a very simple way for us to link a timestamp to a transaction. But unfortunately, in most cases, they're overwritten after just 10.5 minutes. This is because there's an array of 128 Uber blocks, and data is flushed into this every 5 seconds. So after 635 seconds, it will start overriding the first one again. It's under a constant load. One of the interesting things I found though is that under certain pool configurations, if you've got more than 3 disks and a flat pool, then the Uber blocks will last longer, but still they'll only last for a few hours at most. So in practice, this isn't a very useful technique unless you're breaking down someone's door if they're deleting files or something. The Uber blocks will long get over. One of the most useful one I found was the first transaction group ID in the block pointer. So up the top is a abbreviated output of a block pointer from DB. So these DBA entries are the pointers, the actual data. There's 2 redundant copies of this particular pointer. This first value is the transaction group ID. And I found that basically because the transaction IDs are assigned incrementally, there's a directly linear relationship between file modification time and the birth TXT block pointer. So in every single experiment where there was tampering, I could successfully use this to detect tampering. I also observed with the block pointer versus TXT that in large files, sometimes blocks have different transaction group ID values. This is the purpose of the second follow-up experiments to verify this behavior by creating a large file. So this is an example. In this file, there's one block written in transaction group 25, then a second block written in transaction group 29. So this file was last modified in transaction group 29. But if we can find another file somewhere else on the disk that was last modified transaction group 25, then we know that that was the time that transaction group 25 was written. So we know that was the time that this block was written. So this technique allows us to obtain the modification time of the individual blocks of file data in any large file. Large meaning over 128K, because Zettabyte by default uses 128K blocks. This is very useful for forensics because normally you can't get this sort of information. You can only get the last modified time of the whole file. Using this, you can get the last modified time of each individual block of the data. You can also see here, this